Dr. L. Jones Torsius Thos, Professor of Mathematics, College of Engineering Gindi, Anna University, Chennai. He has obtained BSc and MSc Mathematics from Madurai Kamaraj University and PhD from Indian Institute of Technology, Bombay. He has served as NBHM Postdoctoral Fellow at Indian Institute of Technology, Bombay, and then as visiting faculty at University of Tennessee, Knoxville, USA, and Colorado School of Mines, Golden, USA. He is currently working as a professor in the Department of Mathematics at Anna University, Chennai. His research area includes numerical analysis of ordinary differential equations and partial differential equations. He has published more than 25 research papers in reputed international journals. He has visited many countries like USA, UK, Italy, Malaysia to participate in international conferences. He has completed DST SCRB funding project.
Welcome to UGC lecture series on BSc Electronics Practical. Today we are going to see the roots of nonlinear equations. Basically we are going to find a solution to certain types of algebraic, transcendental, polynomial equations. There are so many methods, bisection methods, method of false position, iteration methods, and today mainly we are going to see Newton-Raphson method. It is one of the popular methods to solve a polynomial equation. Straight away we go to the problem. So, the problem of consideration is to find x a real value so that f of x is 0. So, this is the main equation which we are going to consider. The f can be a polynomial equation, or it can be a trigonometric equations, or it can be algebraic equation obtained by all kind of algebraic operations and transcendental equation. For example, f of x could be a cubic polynomial x squared minus 4x minus 9. Now, basically we are going to find the solution procedure for this equation, and f could be x e power x minus cos x. In that situation we are going to solve this equation x e power x minus cos x equal to 0. F could be 2 times x power 5 minus log x minus 6. So, in that situation we are going to discuss 2 x power 5 minus log x minus 6 equal to 0. So, it can be f can be any equations. We are going to discuss the method to find the solution to that equation, basically the roots to the equations. Unfortunately, it is very difficult to capture the exact roots, and this course is a practical course. So, we are going to discuss numerical methods for that. The main method which we are going to cover today is Newton-Raphson method. Okay, so, in any numerical methods, Taylor series obviously is going to appear, and here also consider the Taylor series f of x about a point x naught. So, it is f of x is equal to f of x naught plus the difference x minus x naught times the first derivative. F prime stands for the first derivative plus x minus x naught power 2 upon 2 factorial, which is 2, times the second derivative I evaluated at x naught. So, this is a Taylor series. We are going to ignore the higher order terms of second derivative and quadratic term x minus x squared. So, ignoring that, because that gave higher order error, ignoring that, and we wish to have that this f of x could be a root. That means, this x, the new x could be a root to the f of x. So, we wish that f of x is 0, then you have that x is equal to, so x naught minus f of x naught derivative divided by f prime x naught. So, basically you have x is equal to x naught minus f of x naught divided by f prime. We have an iterated procedure. This particular techniques give an iterative procedure that start with the previous x naught, substitute in this expression, right hand side expression, obtain the new root. So, it is not an exact root, it is an approximate root. So, every time iteratively we go near to the exact root. So, starting from x naught we compute x1, then substitute plug here and we compute x2, then x2 is plugged in the right hand side expression, we compute x3. Like that continuously each times we get a sequence of xn's, and theoretically it is proved that that will approach to the exact root. So, at any time if you truncate it, that will give an approximate solution to the exact root. Basically this method is a tangential approximation. So, that is explained here in the next picture. So, here this is the curve, the black color is that y equal to f of x, and that crosses the horizontal x axis, that is the root which we want to capture it. We want to capture this root. What we do is we start with the point x naught. Okay. Consider the point on the curve x naught f of x naught. So, at that point we are taking a tangent line to that curve. That equation is y minus y naught equal to f prime of x naught times x minus x naught. We want to capture this point. At that point the line meets the horizontal axis. So, the y coordinate of that point is 0. So, I have y is 0, then this equation if I solve I will get the approximate, I will get the x1. Now, from x1 consider the tangent line meeting the curve, I will get the another next point x2. So, likewise we approach, we get sequence of points very close to the root. Numerical example for that. So, let f of x be 3x minus cosine x minus 1, and see we have to identify the starting point. How to identify the starting point? So, arbitrarily we substitute two different values to x. For example, put x equal to 0, I get a negative value 3 times 0 which will be 0 minus cosine 0 which is minus 1. So, minus 1 I get a negative value, and then I will choose another arbitrary value 1, I will plug in there. So, then I get a positive value. So, this given function f of x is a continuous function, it changes its sign between two values 0 and 1. So, by intermediate value theorem definitely there is a root. So, that root we want to capture. So, using the iteration formula. Okay. And of course, f derivative we need it. So, f derivative is calculated and we substitute in the formula. So, this is the iterative procedure, x n plus 1 is equal to x n plus 1, it is equal to x n minus f of x n divided by f prime. So, I substitute f and f prime here, okay. I get this substitution. This is the iterative procedure which we are going to use for our numerical purpose. And now, I just started with a starting point x naught, I obtained x1 the first iteration, and I used that to obtain the second iteration, and I used that to obtain the third iteration, and here I have considered only 4 decimal places. So, it happened to be same value, it happened to be that we are obtaining same value for x3 and x4. So, you can stop the iteration there. So, numerically solving by handy computation you can go up to 4 or 5 iteration, but you can write code for this and you can run it and you can get an iteration up to say 100 or 1000 iterations you can go, okay. And this is the pseudo code for that. I explain the pseudo code. Pseudo code is nothing but something like a flow chart but it is written in an elegant manner, and from this you can get a code by using appropriate data structure and programming language. So, this is the pseudo code which we are going to see. The title of the code is Newton-Raphson method. It requires f of x as input, the function, x naught the starting point as an input, and max iter, it refers to the maximum number of iterations which we are going to use in the code. It can be 1000 or it can be 5000 or it can be 10,000, and there is another value called TOL, that stands for the tolerance value. See, you do not have to go for maximum number of iteration. Sometimes if xn and xn plus r are very close, or if you get same value, you can stop the program. So, for that stopping criteria TOL is used. Okay. So, the input is f x naught maximum iteration and tolerance value. The output is the approximate solution xn plus 1. And here I use a flag. The flag value is a Boolean value having true or false or 0 or 1 value. That helps us to stop the code. If you have same values for consecutive iterations, you can stop the program. So, that will help. Okay. Now, this is the main part of the algorithm, and it is an iterative procedure. So, we need a block structure, and in for loop is heavily used here, because we go up to maximum number of iterations, or before that if you get consecutive iterations, you have a same value or very close value, you can stop the code. So, for that we use a for value. N starts from 0 and n can go up to maximum iteration and n plus plus. Here you have a logical expression max iter and flag. If n is less than or equal to max iter, that will have a true value. If flag is true, then this block will be executed. Once the flag will become false value, then the control will be exited out of the loop, and the flag value negative can be decided when the error xn plus 1 minus xn is less than tolerance. You can stop the program. Okay. So, for n equal to 0, n less than or equal to max iter, flag ampersand, this is the logical expression, and when the logical expression is true, the program will be executed, the block structure will be executed. Once the logical expression becomes false, then the control will be exited out of it and it will go to the return statement. And when will this be having a false value? Both, it should either n greater than max iter or n the flag becomes false value. So, if any one of things happens, the combined logical expression will have false value. So, the control will be executed. Okay. Now, if n is less than max iteration, then we calculate we use the Newton-Raphson formula xn minus f of xn divided upon f prime xn. Of course, here the derivative is not explicitly calculated and mentioned in the code, and when the user writing a code, okay, you have to separately calculate the derivative part and you have to compute this expression right hand side, and using when n equal to 0, we use the starting point x naught and we compute x1. Then again we compare the error between x naught and x1. If it is less than the tolerance value, you can come out, or otherwise, okay, again you go back. Now n will be 2, now n will be 1, because n plus plus, initially n was 0, n will be 1. So, x1 we are calculating using x naught, then x2 will be calculated, then x3 will be calculated, keep on we compute further more iterations. When the 2 consecutive iterations are very close to a tolerant value, then the flag, that value will be false, and now control will go there, and now this Boolean expression is evaluated. Once it becomes false, the control will be exited out of the loop and it will go to return statement. That will give you the approximate route to the solutions. So, once again I will repeat, the Newton-Raphson method, it is a numerical procedure which computes the approximate solution to the root of nonlinear equation. You cannot compute exact solution, since this procedure computes approximate solutions. And second, it is an iterative procedure. So, you can start with an initial value and x1, x2, xn, likewise a sequence of values you can obtain which will converge to the root, that is proved. Further, at the end I will just point out that this method has a limitation. When the derivative evaluated at this point, if it is 0 or very close to 0 and that appears at the denominator, it will blow up. So, which will give wrong value. So, this method has a limitation. When the derivative is non-zero or it is not close to 0, then only the method will work out. So, you have to be careful while considering the problem. The derivative should not be vanished at any of the iterate points. So, I will stop here. Thank you very much.